Maybe just a small correction that I don't know that 6 months at IIT Bombay, it will be 3 semesters basically, total 18 months approximately. It was there. But anyway, thank you very much for the nice introduction. So should I before I start sharing my slides, so may I know a little bit about the audience and with whom I'm talking with? I can see in this one that there are 9 participants. Is it so, or there are some other, or I am not able to see?
No, sir. Actually, there are more than 200 attendees, and the presenters, the nine presenters are 9 faculties, chemistry faculties.
Okay, 9 are the faculty members only. So there are other things which is maybe not visible to me. So, and they are mostly undergraduates or in the postgraduate also.
No, all are UG students, first year BTech students, and
All of
majority have computer science background.
majority have the computer science background and they are the undergraduate first year students. Yeah. So maybe why I ask this thing is basically maybe I'll just try to tune my presentation in that way so that it is a little bit convincing to them. So I have approximately 1 hour time, right?
Yeah,
Okay.
exactly.
Okay, so let me share my screen and just let me know whether it is properly visible at your end or not. So is it visible?
Yes, it is.
And sometimes the slide transition doesn't occur. So just to cross check. So is it the second slide?
Yes, now the second slide.
Now
Slide
I'm on the
number 2.
first. So
Exactly.
now I'm back to the first slide again.
Yeah.
Okay, fine. So once again, good evening, everyone. So I just welcome you to my this part of this lecture, where I'll be talking about the water resource engineering and climate change and some of the modeling aspects. As I can understand that all of you are from undergraduate and first year, you have just started your engineering background. And of course, you should look for some of the environmental sciences application. You might have already taken many courses. You understand by this time the importance of this particular area. And today what I'm going to talk about is one of the very recent focus that both from our society as well as from government side is basically there are some changes in the climate that you observe, and that has some lots of socioeconomic impact at different aspects. Today in this particular talk, I'll try to convey some of the thoughts on the water resources engineering. You know that how important the water is for our socioeconomic development. We can't even think of a single day without it. What is happening is basically some of the things are changing and it requires some special care. So since you are having some sort of computer science background, so I'm sure that some of the things will be useful to you for this course as well as beyond this course whenever you are going to pick up some of the projects somewhere in India or abroad. So I will try to give you some basics. At the same time, I'll take you to some of the cutting edge research domain. I understand that some of the things maybe you people might be too young to grasp it at this moment, but keep these things with you, and somewhere, sometime, definitely will come across to these issues and all. So that time, some of the things may be useful to you. So this is now I'm on slide number 2. I hope it is properly transit at your end also. So this is the approximate outline that I will try to cover, where I'll start with some of the basic concepts of this broad domain. Then I'll talk about some of the rainfall extremes that we have seen in the recent era in the city-based too much extreme rainfall that is happening, and what are the different changes that I'll give you some outline. Then one concept is called the time varying concept in the hydroclimatic analysis, which is basically suitable for this kind of change modeling. Then some in-house developed software kind of hydroclimatic conceptual streamflow model, which is able to take care of the climatic inputs as well as changes in the watershed and changes in the land use, land cover. Maybe there are some of the technical terms, but I'll try to make it as clear as possible to all of you. And then comes some of the aspects of the droughts, its characterization, its analysis. And there are different types of droughts. One is called the meteorological drought, agricultural drought, hydrological droughts. And then there are others also like socioeconomic drought, but we will mainly focus on these three. And then some concluding remarks along with some further reading suggestion. So at the outset, we all know, thanks to the media and there are different news coverage, that there is a significant impact of climate change, and in the water sector it is almost everywhere, starting from the river flow, the snowpack retreat of the glaciers, hydropower, electric, floods, drought, agriculture, groundwater, different types of water use, particularly in the water quality sector, and so on and so forth. So we can't even think of any phase of our life in general, and particularly in this talk we are focusing only on the water, so the water resources sector. So almost there is some impact. The basic major question in this domain is that how to model this kind of hydrologic time series or the data under the climate change scenario. So if there is some change in the climate, what are the impact that is expected and how these things can be modeled too. So my lecture in this lecture, I'll just try to focus some of the part, and of course in the different domain. So what I thought that I will try to touch upon as many areas as possible, so that later on you can select by yourself the area that is interesting or that interests to you, and particularly for your locality. I'm sure that you are from the different parts of India, and at your locality also there are different problems you might have already faced. Some of the basic concept at the very starting, since you are undergraduate students, so some of the things you may be knowing and some of the things you may be hearing from the here and there from media and news. So first, to difference that we almost know from our school days is called the weather and climate. So these two are two different things. Weather, as we know, that it is the atmospheric condition at a particular place over a very short period of time. So this very short period of time, that means it may be at a scale of hour or day or maximum up to a week. So what is the weather today? What is the weather? Weather is changing rapidly. That kind of terminology we generally utilize. Whereas when you call as a climate, it is basically a long-term average or long-term average of the weather pattern over a climatological period, it is called. And this climatological period is generally say 30 to 35 years. So over this long period, if I take the average weather pattern for a region, for a location, for a locality, then we call that is the climate of that particular area. Now comes another two terms, that the climate change is now a buzzing word, and we hear these things here and there almost every news or every day there is some coverage on this one. But there is another term also comes with this, that is called the climate variability. So climate change may be well heard, but climate variability sometimes we mixed with what is climate variability and what is climate change. So these two things basically depends on the which time scale that we are talking about. This is basically a change. So when I call that climate variability, it refers to the variation of the climate that typically lasts longer than individual weather event. For example, it may be so 1 year or 2 years, this kind of things, or couple of years that we take, that how is it changing. So last year monsoon was not like this year monsoon is like this, last year it was not this much hot, this year it is little bit hotter, this year winter has come little bit early. So that kind of things, if we say in terms of couple of years in that scale, then that we refer to as the climate variability. But if we say that climate change, it is basically the same variation but over a much longer time period. For example, for the decades, 10 years or 20 years, or even more. So how the overall pattern is changing over a very long time interval, then we say that we refer to as a climate change. So there are four things in this slide we learned. One is the weather and climate, their basic difference, and then the climate variability and climate change. So overview of this one, if I just see that why these things is important, or what is this actually we generally going to do in this particular area, is basically the association between two major science domain. The one domain is called the atmospheric science, and other one is called the hydrological science, hydrology or water resources domain. So these two are very much connected. So some change in one domain have some impact in the other domain also. And this impacts, this association is basically both maybe very local scale to the very large scale. So that's why if you see on this slide, there are two arrows that I have shown from the atmospheric science to this hydrology and water resource domain. On the upper one, it is shown that hydroclimatic teleconnection. So this tele word, that means these two are wide apart. So the definition wise, I can say that the significant association between hydrologic events and large scale atmospheric circulation pattern, which are widely separated. This widely separated means at a planetary scale across the globe. That is referred to as the hydroclimatic teleconnection. I'm sure you might have heard some of the terms like El Nino. So El Nino is one event in the atmospheric science domain that happens in the tropical Pacific Ocean. The tropical Pacific Ocean, even towards the eastern side of the tropical Pacific Ocean. So now that we generally hear before the monsoon starts and sometimes throughout the year, how is the El Nino status and all we can say. So how is it, why it is important that comes to our knowledge is that it has some impact on the Indian monsoon. So there are some analysis are there. So it has some association with the Indian monsoon part. So you can see that how far away these two incidents are. So one is in the eastern part of the tropical Pacific Ocean, and another one is the India. So in the planetary scale, these are far away from each other, but they have some association. So this kind of association is called hydroclimatic teleconnection. Similarly, it is not only always this much far away, it can be in the localite also. For example, if we say that there is a low pressure domain, so this low pressure domain may be in the scale of, say, for example, 100 kilometer to 500 kilometer, in that range, or even smaller than that. So those are very local incidents, and that is what is called the hydrometeorological association. So that's why the second arrow is shown between these two links. So it is the significant association between the hydrologic event and local meteorological variable, and this thing is referred to as hydrometeorologic connection or association, that we call it. So what we understand in this particular slide is that there are two major domains of the science. One is atmospheric science, other one is the hydrological science, and these two are very closely associated with each other, and this association is valid both at a planetary scale as well as at a local scale. If it is at the planetary scale, then we call it as a hydroclimatic teleconnection. That tele word comes here, I want to underline. And second thing is a very local one, which is we call as a hydrometeorological association or connection. And these are some of the four things that happens to influence on different hydrological phenomena, and rainfall is one of them. And of course, it is, we have started already seeing there are some extremes and all that we have seen. So both the things are important for this domain. Now, how to model it? So overall modeling strategy can be seen into two different parts. The first basic understanding, as I was trying to trace upon in the last slide, is that the hydrologic variables are significantly forced by atmospheric phenomena. Whatever is happening in this atmospheric circulation or different changes in the atmospheric domain, it has some, those things significantly force the variability of the hydrologic cycle or hydrologic variables. So this is already known. So these hydrologic variables are significantly forced by this atmospheric phenomena is already known. That means if there is a change in the atmospheric pattern, so that change might be reflected in the hydrologic domain also. Now, if I see the modeling strategy of these things, there are lots of models are available, means the local model, large scale model, entire planetary scale model. There are different types of models are there, but what I am trying to differentiate in this slide is that they can be overall can be grouped into two major groups that I have tried to show in the blue arrow and in the green arrow. On the left hand side, you can see that there are different model, the general circulation model, or it is also known as the global climate models. Both are abbreviated as GCMs. So these things are as a planetary scale or the global scale model, and these things really require some sort of supercomputer kind of computing facilities to run that kind of model to see that how the atmosphere or how the climate is going to change or going to respond to some change in terms of some of the components of this atmosphere. For example, there is an increase in the greenhouse gases, then how that thing is going to impact in the change in future. So this kind of run, if we do it through this general circulation model, and whatever the simulation result we get, we try to analyze it so for its impact on the hydrologic or hydrologic domain. On the other side, there are some phenomena that we have seen in the atmospheric atmosphere, and we see some of the responses in the hydrologic domain. And these two things, the together we call it as a hydroclimatic or hydroclimatology. So this hydroclimatic association are generally taken through some stochastic analysis. The stochastic analysis means there are this association is modeled through some analysis. And why is it stochastic? Because there are lots of uncertainties are there. So it is not a deterministic model kind of thing. So deterministic model means that there is one input for a particular input, there is always a particular output. Just like you know already that y equals to mx plus c is the regression equation. If I give some value of x, I'll get some response y. This is the example of deterministic equation. So, but the stochastic equation means it is no, it is not. There are some uncertainty associated. So always, whatever the output that we get, there will be some uncertainty associated. So we need some sort of stochastic analysis of these two phenomena and try to identify, try to model it. So through some probability or statistical model to find out what could be the changes in this atmospheric that has some impact on this hydrologic variables or different climate variables also. So this what I want to show in this slide is that there are two major group of the modeling strategy that we can take up, and this can be grouped like this. Both of them have their own merits and demerits, but in general, in this entire domain of hydroclimatology, there are different challenges are there, mostly from the computational challenging point of view. Since you are from the computer science background, some of the things you will also come across that how to run a big model, that nowadays era of the big data. So it is very well used in this domain as well. So the challenges, some of the challenges are outlined here. The first challenge is that whenever we talk about some cause-effect relationship, so this is the causal variable and this is the effect on it. So there is a dynamic nature of this relationship. So this dynamic nature means it is changing over time. So whatever the relationship that I identify, y equals to mx plus c, for example, just a basic example I'm just putting into. So that m, the parameter that I estimate, that parameter may change over time. So the relationship that we are going to model, that has a dynamic in nature. Second challenge is that there is a lots of uncertainty associated with it. So we need to quantify that uncertainty associated with that model. Third one is maybe a little bit more advanced statistics knowledge is needed, but it is called non-stationarity. But if I just give you some examples, so whenever there are some changes in a time series, I can tell you that what is time series. Time series is basically the record of a variable arranged in a chronological order. So it is just, for example, daily temperature I'm just measuring, and for each day I'm recording it and drawing a nice line. You might have seen that the electrocardiogram that comes out from a machine when a patient is going through ECG. So that kind of diagram, that kind of information that comes is recorded with respect to the time is called the time series. And there are two types of time series. One is called stationary, other one is called non-stationary. The stationary means it remains almost same within an envelope, so it doesn't change over time. And there are some time series, statistical properties can change over time, and those time series are called the non-stationary. For example, if you take the global temperature, global mean temperature, and you might have heard the term from the news that the global warming, so it is increasing. So if you see from some web source or some news that how the temperature is increasing, then you will see that there is a clear visible increasing trend mostly after 1970s or so. So that kind of time series is called the non-stationary time series. So now when we try to model some time series which is remains same over time, so that is one type of issues, no doubt. But if there is change in over the time, it becomes a non-stationary time series. So that consideration of that non-stationarity itself is a big challenge in the computational domain. Next comes from the large scale phenomena to the basin scale phenomena. So large scale phenomena, what I mean is the entire continent, entire India or entire hemisphere that I can consider, that I can run. But the basin scale here means it is basically a river basin. So I just want to I am interested only the river basin like Narmada or Mahanadi or say Godavari, like that kind of thing. So it is not the too large scale. So I need to know what is happening to this smaller scale. Now it has been, we are even more ambitious to find out at a pixel scale. You know already what is pixel in a photography, and you all have very huge, good quality cameras in your mobile. So you know what is pixel. So we are now interested to know that what is happening at a pixel level. So now when I want to transfer the information from a large domain to a small pixel domain, then that itself becomes a challenge. And this is necessary for this one to understanding of this this climatic phenomena and its impact in the local scale. That is really a big challenge. So ultimately, all these challenges, when we just talk about, particularly in the water domain, we try to improve the prediction. How is it going to affect the society? For example, this much amount of rainfall in a city like Hyderabad, how much it will cause the social damage, how much it will cause the water logging, how much the society will be cautious about. So that kind of improved prediction performance, if we can provide, then it will be useful to the society, as it is already we started feeling that its importance in some of the recent phenomena. Now, some of the again, these are all some basic concepts just I want to convey to you. The one thing is called the downscaling. This downscaling means when there is a bigger domain and I just want to take it down to a small scale phenomena, that is what is known as the downscaling. But maybe the cutting edge research domain, if we just talk about, always there is a thinking in the researcher's mind. Now the thing is that whenever I am trying to take this to a smaller scale, so there could be some time variability. So time variability means over the time, that kind of relationship or that kind of strategy, that kind of methodology over the time may gradually change. So whatever the information that I want to downscale, for example, this downscale, the low resolution GCM, just now I told you what is GCM simulation. That GCM simulation, when it covers the entire globe, it gives an output at a range of say 250 kilometer to 350 kilometer. You can imagine how far. So one information at Hyderabad, second information maybe in Bangalore. So now, but in between, I don't get any information. So I need to downscale it to some scale, for example, 10 to 50 kilometer or even lower. Nowadays, we are more ambitious to have even lower. So this transition is what is known as downscaling. And there are two different types of downscaling are there. The first one is called the statistical downscaling and second one is called dynamical downscaling. And both the things are computationally intensive and they have their own merits and demerits. So here I have just tried to put down what are the things. So whereas the statistical downscaling, it depends on the relationship between the causal variable and the target variable, and it is computationally less intensive. At the same time, the dynamical downscaling, if I see, it uses another type of model which is called the regional climate model. Earlier I used the word called the GCM, the global climate model, and it is regional climate model. So which is forced by the output from a GCM and it runs in a local scale, but it is computationally huge demanding. So it has their own merits and demerits indeed. But the basic thing from both the things is that there is stationarity. Again, the word came to our discussion. It's called the stationarity. Stationarity means the relationship or whatever the methodology that I'm trying to develop that doesn't change over time. But again, now in the era of this climate change and its impact, this may not be stationary anymore, so it may become non-stationary. So is there any non-stationarity in this relationship also? And if it is yes, then very recently we are trying to think about the time varying downscaling model, whatever, whether that could be more suitable or not. But for you at your stage, what I want to show in this slide is that what is downscaling? Downscaling means from a low resolution but a larger area covering information, we generally go to the high resolution. It may be the smaller, but the resolution improves. So this kind of transition, it is called the downscaling. Another important term that we utilize in this domain is called the bias correction. This bias correction, first of all, you have to know what is bias. So bias is the difference in the mean and the variability between between two things. Here I have written a more technical definition. It's the observed data and the climate model simulation. But any two information that I get from two different sources for the same for the same variable. For example, the rainfall, I am measuring with two different instruments. One is the sensor based, another one is maybe based on some old rain gauge stations and all. So if there is a discrepancy between these two in terms of its mean and variability, then we call that there is a bias. Second thing is that suppose that there is a model output that is coming in and there is an observed record for that one. So if there is a discrepancy between these two, we say that the model output is biased for something. For here, one example is given here. The blue line you can see, and there is a red or orange line at the bottom. So there is a gap between these two. So basically, whatever these two things, it may there are two things. One is the overall mean or average. There is a gap between these two, and second thing, their variability, the range is also different. So for the blue one, range is small, and for the red one, the range is high. So now somehow we have to match these two, and basically it is on the right hand side, it is showing that how the match could be. I'm not going to the details. This is but you might have seen from your school days that how to fit a distribution, and this is how so after I do this, so maybe if I don't even want to know that how it is work for the probabilistic scale and all, only thing the bias correction means it is an approach that corrects the climate model output using the information of the bias assessed during a reference period. This reference period again is the climatological scale of 30 years or so. Suppose that this is a 30 years time frame, and we have to make sure that the simulated values more or less matches with this one in terms of its mean and its range or the variability that we call about. So these two things, when it is matches, that process is called the bias correction. So there are two things we understood now. One is the downscaling. Downscaling means when there is a spatial scale or the spatial resolution is very low, that we want to make it a high resolution. And after that, if there is a bias between whatever the simulated results and that bias we want to correct it, and that through some bias correction procedure. With this background, let us think some of the recent phenomena, and this is very recently explored. It is called the southward shift of precipitation extreme. So overall in India, if you just see that there are many cities are all of a sudden they experience a very heavy rainfall, and there are some examples are many. We have seen that very recently even in the Hyderabad, very recently. Before that it was in Delhi, before that it was in Assam, Uttarakhand, Mumbai, and all the big cities, Kerala flood last year. So there are lots of this kind of phenomena we generally hear. So this is called the extreme precipitation. This extreme precipitation means that is something above the expectation, above the historical record. All of a sudden it happens, and it creates some social nuisance, and there are lots of loss of life as well as property. So those are the extreme precipitation pattern. Now in this one, what we have very recently found out that this kind of extremes are basically shifting towards the southern part of India. But the thing is that there are, if I just take, so you know that there is one organization that is called India Meteorological Department, IMD. You might have heard it from the news, and also they give us so many forecasts and all. So with them or other agencies also, we have almost more than 100 years of rainfall record is available. So now if I take the rainfall record for each and every location and find out what is the trend, we can see that there are some area that is increasing and some area that is increasing. Some one of the screenshot it is shown here for one variable means one index, that is called the variation index. So that is at some point it is increasing and some location it is decreasing. Now, what is happening to understand that how is it changing? Is it changing everywhere, irrespective of their location, irrespective of the time, or it is changing there is an overall pattern that we can identify? So that is very important to understand, to be more prepared for the future. So that is the overall objective, and these things has been done. Little bit of mathematics I'll just show you here. And suppose that this blue line is the rainfall one, and I just want to make decide some number from this data, and that number I want to decide in such a way that 95% of the data is below this and only 5% data is above this. So it is very easy. If there are, say, for example, 1000 data points are there, so that means 950 data below this and only 50 data is above this. So if I just take this one, I can find out that threshold, and that threshold I just give a notation P95. It is called the percentile. So percentile you already know. So this is the P95, and all the values above this P95 are shown here. You can easily identify here. And if I take a mean of that and I designate that number as a M95. So M95 is the mean and P95 is the threshold. Similarly, I can identify the P99 also. The P99 means 99% of the data below that threshold and only 1% above that, and above whatever it is, if I take a mean, that will become M95. So here it is shown 2 threshold and 2 mean magnitude is shown. So P95, P99, and then M95 and M99. Their definitions are shown here. So why I need this thing? These are basically some of the extreme threshold. How the extreme precipitation is changing is our focus all over India. I'm not going again so too much details of this discussion. Only thing, some of the findings that if I want to convey, if I just see that one up to 1970 and after 1970, there was the perceivable change in the climate system that has been observed in the 70s. You know that lots of industrialization is started from there. Visible global warming has been started from that particular decade. And we can see that some different changes in this one. Here we have just shown some of the changes in this in the mean daily precipitation pattern all over India, and there is a clear difference between these two before and after 1970 is visible on the top row that I mean here, A and B. And C and D is basically I identify those states where it is not increasing. It is not decreasing. It is increasing. Take all the states and take a mean, and take all the states where it is decreasing, which is E and F. So we can see that here the overall thing that we see that wherever it is a decreasing thing, it is decreasing in a much faster rate than the increasing thing. So this is for irrespective of which place. So it is an in general all over India scenario that we have shown here. But if I go for a little bit more details, each and every pixel now, if I see it, and we can see that there are some part it is really increasing, some part it is decreasing, two different colors you can see here. And these are all can be tested statistically whether it is really increasing or not. So it's really increasing or not means if I get a slight trend, should we say that it is a positive trend, or slight negative trend? Should we say that it is a negative trend is really decreasing, or it is just a random from the data? So there are some tests statistically you can check whether that trend is significant or not. It is called the significance test. So that's why accordingly there are three categories are there in these plots has been shown. One is increasing. Increasing means it is significantly increasing. Decreasing, that is significantly decreasing. And where there is no change, it is insignificant. Those are in the white color and all. So what we have seen, there are the top row is basically from 1930 to 1970, and bottom one is 71 to 2017, recent one. So there is a change in the northern part and southern part. Of course, these changes are staggered. That division has been shown here. So there are some changes between the northern and the southern part. So where it is increasing, how much area it is increasing, what is the that mean M95, M99 that we have shown. So how is these things are changing in the past and after after the industrialization, after the perceivable changes that has been noticed, that is 1971 to 2017, and before that long past means 1930 to 1970. So whatever we have seen that there is a change in the M95 in the range of plus minus 20 mm per day, and M99 is plus minus 30 mm per day, and this increase and decrease that is shown in different color range is that almost it is 60% area. So far as P95 threshold is concerned, so far as and the P99 threshold is concerned, 45% of the area of the entire domain it is increasing. Now, if I just want to see it, that just to quantify the how these changes are, it is basically approximately the south of 20° north is showing more increase than the northern part. The question is why is it so? So is there any reason that we can find out? So that does it indicate that the South Indian cities will be more vulnerable to the extreme rainfall, or not only the cities in the other parts as well? So what are those parts that is more vulnerable to this increase? So for that one that I was telling there, that there are some GCMs, some RCMs are there, and there are some source where these models are being run. Almost more than 30 GCMs are run all over the world, and we could access those data. And this IITM is our organization. It is called the Indian Institute of Tropical Meteorology, where it is kind of it is in Pune. So they also are responsible for some of this data preparation and disperse to the scientific community. So we have taken 7 such model combination GCM-RCM models and do this analysis how these changes are in the past and how it is going to change in the future. And this is some of the snapshots are shown here. And so wherever it is increasing and wherever it is decreasing, these things are basically shown here. And out of this, in the lower panel, what you see, the different models basically gives different output, and that is one of the biggest thing of this uncertainty analysis. And sometimes the general community, they say, okay, my God, this model is saying that is increase and that model is saying it will decrease. So what is this case? These things basically what happens, this kind of models, they are basically built upon different assumptions. Different assumptions means those assumptions even include how the human being will behave so far as their consumption of the fossil fuels are concerned, and those things are taken care of. So of course, that since the assumptions are different, model outputs are different. So what we have to do, we have to go with the majority. So this lower panel is showing for each and every pixel how many models are agreeing with each other. So obviously the 1 to 7, as I showed that there are 7 models. So sometimes this kind of analysis, when there is a lots of uncertainty involved, so we have to see that what are the majority of the model tells. So this is one of the things. So this slide is showing with respect to the mean where it is underlined, and similarly other things, the M95 and M99, those things are shown here. How is it going to change in the near future, mid future, and far future? And near future means 2006 to 2100 is the entire period, and there are 3 epochs are there: 2006 to 2035, 2036 to 2070, and 2071 to 2100. So if we just see that how these things are changing, then we can have a look that it is more towards the southern part of India, and of course the Himalayan foothills, that is showing some sort of increase. And within the South India also, the Western Ghats is showing more increase of this extreme rainfall. Similarly for the other threshold also that we have seen, and this increase is as much as, say, for example, in the range of 40 mm per day or so at some of the location that is shown. But as you know that this monsoon system is not only the Indian phenomena, it takes the entire southern part of India. It is not only that India that is going to face this kind of changes. There are other countries like Myanmar, Thailand, Malaysia, etc. And the western parts of Indian Ocean region also will have some sort of changes. And on an average, 18.5 mm per day for the. There are different, again, the climate change scenarios are also there. I'm not going to that details, and the only thing that RCP 8.5 is the worst scenario possible in future. So if we consider that one, that much increase is supposed to see. So far we have seen that what is the change that can happen. Now the question comes that so I'm not going to further details of this on how these things will change. What is the changes with respect to the previous time? So those kind of analysis are there. But this part I'll conclude with one more discussion with the question that is we always ask in the science that why this kind of changes are there. So for that type of analysis, we have done some sort of analysis which is called the water holding capacity of the warm air. You know that when the air is warming up, it can hold more water vapor, and if it can hold water vapor, it has a tendency to means concentrate at a location. That is what is called the moisture flux and moisture convergence. So I'm not going into the details once again. The moisture flux means it is basically from how much it is coming in and how much is going out. Again, in a computational domain, if I just see in a two-dimensional case, that is just a square box, and how much is coming in, how much is going out. And second thing, it is called the moisture convergence. The moisture convergence means what is the storage in that pixel. So whatever is coming in is not going out, and this can be done through that wind speed and relative humidity. These two informations are needed, and so we can find out that where this convergence is more. And this is what we have seen is this one, is that whatever the trade wind in the south means that southwest monsoon, it is basically concentrating towards the southern part of India. And that is what is happening. Again, there are other large-scale phenomena, as you know from the media, that El Nino. There is another incident. It happens over this tropical Indian Ocean, that is called Indian Ocean dipole. So that Indian Ocean dipole causes that eastern part and western part of tropical Indian Ocean to warm up and cooling down, and it is linked to that Indian Ocean dipole, that how that phenomena is causing this kind of moisture convergence towards the southern part of this peninsula. So that's basically the approximate reason. I understand that it is a little bit of a higher side, so I'm not going to the details to that one. So you can just remember from this one is that there are some changes in this extreme pattern. Mostly it is shifting towards the southern side, if I take the entire India as a concern. And the reason behind this kind of thing is that there are some changes happening in this tropical Indian Ocean, and that changes is causing the more water convergence toward the southern part. And within the southern part of India, the Western Ghats is most vulnerable, and the Himalayan foothills also in the northern in India. And some of these incidents we have seen already in the recent past. So that's all about this discussion. I'm not going into those details, and there are some is there for the further reading and all. Next, I'm taking you to the another concept. It is called the time varying concept. Time varying concept, it is called that over the time, the things are changing, whether that how to model those things. Again, I'll just give you the only the overall background to this one so that you can have a look at a later stage if you become interested. So here what happens. So if I just start from your school knowledge, that is y equals to mx plus c. It is a simple linear regression equation, and there is a multiple linear regression is also there. So there are different inputs are there, and those different inputs are, if I just consider, I'll just take you directly to that slide so that yes. So this is a presentation. You may not find any linear regression here. There is no problem in it. But just assume that this lower part is basically your y, and there are three x's are the x1, x2, x3 are there. So what we do generally in the traditional modeling thing that we generally use all three information and find out what is the target. But you know, over the time, those things we can just say that no, I don't need. So some of the connections are basically really not needed. And you know, so for example, it happens in the social life also. Suppose that there are four friends are there. So is it that all are connected to each other with an equal strength? It may not be. And sometimes I'm just putting it very lightly. Suppose that if Mr. A is there, so relation with the Mr. C changes, and if Mr. A is not there, then Mr. C becomes more important. So this is a very loose comment, but at the same time, what in the mathematical domain also sometimes some of the inputs becomes more important, and over the time that relationship may also change. And this is what is in the mathematical domain, we call it as a time varying concept. And this time varying concept, particularly in this climate change domain, it is very important. So over the time, we have to just check whether or recalibrate our understanding is that whether there is any change or not. So this is what is the overall time varying concept, which is gradually becoming very popular in this domain to capture the time variability or the change between the variables, whatever the relationship is. I'm not going into the further details of this domain because it needs a little bit more statistical knowledge, like more statistical knowledge. Even within the statistical knowledge also we need some cupola model to understand their modeling and not. But what is the basic take home from here is that if I have two options. One is called the time, the other part is called the time invariant, whatever we know in the traditional thing. So I can have that traditional model, and or I can have a time variable model. So these things, whatever I'm showing now, I'm just skipping these things. I'm not discussing all these parts. I can directly show you some of the results that how it can be useful in this kind of domain. For example, this is one thing. So okay, fine. Before I go to that comparison, one more important thing here that I need to say. So now it depends on the how soon that relationship can change, right? This is also another concern, and it depends on the how dynamic or how volatile that friends are. Right, some friendship are lifelong, some friendships are temporary, that kind of thing. So here also in the mathematical model domain is also that some of the problems, it may be very dynamic, that it requires more frequent recalibration. So I have taken here that again the Indian summer monsoon rainfall as an example, and it has been shown that 3 years is the time is that once I establish some relationship, after each 3 years I have to relook it and see that there is any change or not. Otherwise, model will start performing gradually. It will deteriorate its performance. This is one, and that so every 3 years that is we call as the optimum recalibration interval (ORI). So that is the 3 years, and if we use that concept or don't use that concept, what is the changes between these two? That has been shown in this slide, where you can see that if we just use the time varying model, its performance is more, and it has been quantified also. It is as much as 64%. I think it is written here to be specific. Here it is that to be specific, 64% more accurate performance. So far as I'm just talking about this Indian summer monsoon rainfall prediction, it is possible using this proposed time varying model. Some of the modeling thing that we have developed here is the in-house software. It's called that hydroclimatic conceptual stream flow model. Again, some of the basic concepts I should give you. So any model means there is a system, there are some input variables, there are some output will come up, will be there. So in this, when I talk about a watershed model and all, there are some hydroclimatic variables are the input, and we get the river flow, we call it stream flow also, stream flow or river flow, groundwater, evapotranspiration are basically its output from the system. Now the thing is that when we talk about the response from the climate change, how is it changing these hydroclimatic variables so that the output, the stream flow, available water resource also will change. But the question here is that the watershed may also change. So this is a time varying concept again is important in this case as well. But the question here is more important that it is not only that the climate is changing, the pattern of the basin is also changing. For example, in your locality also at your childhood, you have seen it is some type, and more you are growing up, you see that it is changing. So more and more flats are coming up, more roads are coming up. There are some areas which are earlier non-accessible, now it is becoming accessible. Human population is increasing. So all those things are there. It is causing the change, the characteristics of watershed also. So when we talk about the climate change model, and it has what is the response of a watershed, we have to remember that the watershed characteristics is also changing in the scale of 30 years or 50 years. It is obviously there is a significant change. So over 30 years it will also change. So the idea here is that whether both the things can be simultaneously considered or not. Again, I'm not going again to the details of this one, but the good thing for this one is that we already have developed one GUI known as the graphical user interface. So you can download it from my website and you can run it whenever. So we're using some data and all. So again, these are the details of this model, and here is my website from where you will get, you can download it. Both Windows and Linux versions are available, and it is free only for the academic purpose. So of course, you can utilize it for your own watershed at your locality and all that you can check. But obviously you need some more knowledge, some more. There are some help files are also there, how to run that software, and at the same time how to prepare the data files for that. But here I understand that so far as your focus from this course is concerned, is that whenever there is a change, particularly in the environmental science that we are talking about, so the change is not only the environmental change. The change could be some sort of the human induced changes are also there, and which are also significant, and sometimes we ignore that, and sometimes we may not be in that luxury to ignore that kind of thing. So this model that I'm talking about now, the ACCS model, is one such thing that where both the effects are basically considered in these things for the basin scale stream flow prediction. Yeah, there are some, those descriptions are still going on. Now we have whatever the small time we have, we'll just discuss about some sort of the droughts. You know, the droughts is basically the shortage of water, and this shortage of water can be as notorious as flood also. Sometimes what happens, the floods are visible, you know, we can see the media covers, we can see lots of water, people are suffering, and all those things are visible. But sometimes the suffering of the drought is not visible. Why I'm saying that is not visible is that key, until and unless I am the victim of that reason, I'm really not worried about. The moment I open the tap, I have sufficient water to use. I don't worry about it. But the farmer who is standing in the middle of his field and he's seeing that there is no rainfall, no water supply for his crop, that agony is very difficult to realize so far as the droughts are concerned. But it has a significant impact on the socioeconomic status of the country, and there are some records in our, if so far as our country is concerned, it can even slash the gross domestic product, that is GDP, if there are some droughts one after another it comes. So it is very important to know the drought, analyze them, foresee them, or means forecast the status, then take some suitable mitigation strategies. As I was telling, there are different types of droughts. In this one, maybe useful to you is that here I just noted the 4 different types. One is the meteorological drought, agricultural drought, and hydrological drought. So, so far as the meteorological droughts are concerned, it is the shortage of rainfall, and agricultural drought is the shortage of soil moisture. Hydrological drought is the shortage of stream flow or the reservoir storage or groundwater. If there is a shortage, those are called the hydrological drought. And socioeconomic drought is basically the combination of all 3 things when it is affect the socioeconomic welfare and the living of that particular locality. That is called the socioeconomic drought. So the drought is one of the least understood natural hazards, and it is called the creeping in nature. The creeping means it is very slowly it comes to the society and affect it. So that is why in this era of this changing climate, its assessment and management is very challenging from different perspective, different point of view. We'll discuss very little about all these 3 types of drought. The first one is the meteorological drought. As I was telling, it is a shortage of the precipitation. And shortage of the precipitation means if there is a locality, I record the rainfall, I do some sort of analysis and find out that what is the index. And it is basically we are talking about some of the index, how to characterize it. How can I say that what is the type of the drought? And it is called the SPI. It stands for the standardized precipitation index. This standardized precipitation index is basically the index that is developed from this rainfall, and from there it has to fit some distribution. And I may not go into the details of this mathematical part, but some of the discussion I can just continue with this one. You know that so far as the India is concerned, it has a strong seasonality that you already know. You know that June, July, August, September we get the maximum rainfall, and rest of the months, rest of the 8 months we generally do not get much rainfall, except that southern part of India where there is a effect of return monsoon also in the November, December. So that means the Indian thing, there is a strong seasonality. Whereas if you go to the US, there is no significant periodicity on this. So here we have just shown that in this one. So this drought characterization for this Indian context, that if we just talk about, maybe instead of standardized precipitation index, the standardized precipitation anomaly index is more important. As I was telling that how to characterize it, there are some of these mathematical parts are there. I'm not going to that details. It is basically only thing you can remember that it is basically some sort of standardization of this local rainfall, and find out that how if there is a positive value, then it is the above normal rainfall. If it is negative value, it is a drought kind of situation. But what is not considered in the traditional SPI is the local climatology is not considered. But you know that our Indian rainfall is very unique and it has a strong visible seasonality. So that seasonality, that climatic information, if we just put into in terms of this monthly rainfall here in this equation, this xj bar is the rainfall, then it becomes more useful and more meaningful so far as the Indian context is concerned. So it is recommended to use the standardized precipitation anomaly index for to capture this local climatology in this drought characterization. There are some discussions are there. I'm not going into that details. Some examples from the previous one why this thing is important and all. Next comes that agricultural drought. Again, some of the basic concepts only I'll just tell you. The first one is called that again, I'm just taking you to the concept of the time series here. So the line that you see here, this is a time series. For example, this is the soil moisture time series, for example, and there is another, there is a threshold, you know, it is called the permanent wilting point. This permanent wilting point is the threshold of the soil moisture. If the soil moisture fall below that threshold, the plants cannot extract any water. So that is a kind of, and you can say that is the initiation of the drought. So the soil moisture falling below that PWP is dangerous for the crop, it will die. So that is why, so when it is above this one, it is called the satisfactory. When it is below, it is not satisfactory. So for a locality, how frequent it goes up and goes down, that we have to check, and how the soil moisture changes and all. This is one of this analysis, and there are different statistical terms. One is called reliability, resilience, and vulnerability. Those can be extracted from the soil moisture series to find out what are that that index, that drought management index that we are talking about. Again, those mathematical stuff I am not going in, and this is the index, basically the drought management index is the probability of the resilience, some combination of the resilience and vulnerability basically. But what does it give? It gives an indication of the drought propensity of that area. You know, I have picked up some 5 regions all over India. One is from the northeast, one of the western Ghats, central part of India, Rajasthan, north part, and it has been validated that it is properly capturing the drought propensity. The propensity means that how drought prone that area is. So of course those things are visible, so that if one area is more drought prone, we have to be more careful about that area. And over the time, for a particular region, if it is gradually becoming drought prone, if it is gradually becoming more and more droughts are expected there, then the long-term strategy has to be taken. And that's why this index name is the drought management index. It helps us to manage the drought. So again, there are some changes how this index is changing all over in India, and their trend also, that how it is changing. And then the analysis is over the entire globe for the different parts, how is it changing. So there is a visible change in future between the southern part of India and the northern part of India, apart from other regions in the world. Okay, fine. So that's all about this agricultural drought and the hydrological drought. Here again, as I told you, the hydrological drought can be a stream flow with respect to with respect to groundwater, with respect to reservoir storage. Here we are talking about the stream flow only. And here one analysis that has been shown that how the drought can be predicted. So here it is just 1 month ahead. Can I say something about this drought? So the hydrological drought in a basin. So the goal is called, the new term is called the drought triggers. Drought triggers means what is the climatic condition this month, so that it will be telling something about the next month. So we have taken 2 watershed in US. This study was done in USA. So we have taken two watershed, and just our question is that what are the different variables that I can see this month, and I want to say something about what is going to happen in the next month. And this set of variables that is able to tell something about the next month's drought, that is what is called the drought triggers. Again, the details I'm not going into it. I can just directly take you to these results. So here you can see that we have taken, in this case, that 7 variables we have taken: the soil moisture, precipitation, runoff, evaporation, temperature, sea level pressure, and wind speed. And out of these 7, for those particular watershed, we have seen that soil moisture, precipitation, and runoff is giving more informative result. That's why this ribbon is more. So how to read this one is that, and the x-axis is the 12 different months. So these colors are basically shown in this color bar, and this D0, D1, D2, D3, D4 are the different categories of the drought. So as the number increases, it is more extreme drought. So these colors are basically linked to this one. So if the soil moisture status is this, if the precipitation status is this, and if the runoff status is this, then in February, what is the drought? What is the drought category that is expected? That is one of observation. Second observation is that these 3 variables having a wide band, whereas the evaporation and other 4 are not having that band. That means these are a little bit of not sensitive that much as compared to the others. So in this basin, the soil moisture, precipitation, and runoff is giving more information, more informative so far as the drought predictions are concerned for this one. But it may change. If I take another watershed, I have to redo this entire analysis and want to find out that for that particular watershed, what are those variables that are more informative, so that forms the drought triggers. So I can say that those are the drought triggers. Then and then we can just say that those information, if I know for this current month, the next month what is happening. So if we can tell that one, then it will be useful for the drought preparedness and other things. So there are so I'm not going to read all these concluding remarks. You have just heard that there are different basic things, starting from the weather, climate, then downscaling, bias correction. Then we discuss about something about the precipitation extremes, how the India is facing and going to change in near future. Then we have seen some softwares, how to take care of this, both the changes, climatic change as well as the watershed change, one of the things that a link I gave, and then I came to the drought again. So the drought again, there are different categories of droughts are being discussed. So there are some of the published papers are there. I think your teachers, your professors can guide you. What are these things at your age? You may not know all these things, but these are available. Sometimes some of this, the southward shift of this precipitation extremes that I was discussing, it came even in the news also. Different leading newspaper covered that story. So those kind of things, those kind of resources are also available. Now I have maybe 5-10 minutes available. There is one book authored by me. Some of the techniques are available in this book. It is called The Statistical Methods in Hydrology and Hydroclimatology. It's published by Springer. So some of the tools are available in this book. Thank you. And I'm just stop sharing my slides. And if you have one or two questions, I'll be happy to take, or it is over to the organizer, the way they guide now.
We have few questions, sir.
Yeah, so is it on the chat window, or how can I see those questions?
It's in the chat window, question answer window.
Okay, I can see. Has the event started? Those are, I think, the initial queries.
Last one.
Okay, I think Pratyush Puri, right? Pratyush Puri Goswami, that question? Yeah, good evening, sir. I want to ask that if at any place the climatic condition is changing in very frequent manner, then how it could categorize? I'm afraid I understood the question fully, but let me understand. Let me first of all reframe the question, and then I will have some light. So, what do you mean that climate is changing very frequently? So, very frequent. Do you mean that in the scale of days or weeks or months or years, something like that? I think so. If you are thinking that it is changing as frequent as the day, so it is not climate, it is the weather that is changing. If you just say that it is changing over the years, then it is again not the climate change, is the climate variability. And if it is even longer, then it is, I categorize as a climate change. But I think your more important question is that how to model them, how to see that. As you see that there are lots of challenges at that starting itself. I just tried to underline some of the issues. It is in the dynamic nature, and that dynamic coefficient is very high, the way you are just explaining it in here. So obviously, the more dynamic the weather is, or more dynamic the conditions are, it is more challenging. And of course, we have to take up the things, the model and all. But the challenge, most important challenge in this thing is that what are the information that we have? Do we have the sufficient record that is available? So if we have the sufficient record of the data from the other basic climatic variables, then this kind of challenges are a bit easier. I'm not saying that easier, but bit easier to tackle if we have sufficient information from the local thing. Particularly say that there is a cyclone is coming, and we generally try to predict that where it will hit and how it will move after it hit, after it make the landfall. So that kind of thing, you can imagine that how frequent or how close or from a dense network the data is needed for that kind of prediction. But I'm sure you are not raising that much dynamic events. Gradually it is changing. But obviously, I agree with you. If it is more frequent, means the challenges are more.
So probably as of now, we are not able to see more questions, but certainly we'll be getting some questions. If we get, we'll be coming back to you, sir. Probably
Sure.
they'll be mailing to you, and
yeah, definitely.
Sir, one more question has come. Sir. We'll take this one as the last one, probably. Sir,
okay. Yeah, I can see that one. It is, I think it is Govinda Rajula Chandrasekhar. Sir, as you said, moisture convergence is moving towards the southern part of India. How can it have an impact on the agricultural sector? What steps can be taken in order to save ourselves from those effects? Yeah, very big question, no doubt. Very big questions in the sense that is, you see, the moisture convergence is moving towards the southern part is not a very correct sentence. It is what I can say that the moisture convergence is more on the southern part as compared to the northern part. You know, the more less, these are all relative or the subjective words. So always it has some comparison. So here we are comparing with respect to the many parts of the northern thing. So it is more on the southern part. I just a little bit correction on your first sentence. Now the thing is that how it will impact on the agricultural sector. Now you see this analysis we are talking about the daily scale. So daily scale means there will be some impact on this daily extreme rainfall, and of course you know that if there is a huge rainfall on the agricultural pasture, there will be some flood and those things. But what steps can be taken in order to save ourselves from these effects? I think it's means in general answer could be I don't have a very crisp answer for this one, but what I can tell you is that is a proper management strategy is basically the way forward that we can adopt. But you know that so that the excess water can be stored properly, can be managed properly, and during the lean hours those water can be utilized. But it is easy to say and very big questions to implement these things. Only thing is that whenever we are raising this question, we have to keep in mind that these incidents are for a couple of days, whereas the water requirement is for the rest of the years. So you can now imagine, you can just imagine what is the scale of the management practice that we have to adopt to tackle this kind of situation. Yeah.
There is no more questions.
Okay. Fine. So I think I can some of that thing previous to previous. Sir, kindly share this PPT, not recording. It's okay. So I think I can just share the PPT with your organizer, and he can circulate to you. And there my contact details will be there. So definitely you can contact me. Whatever time and my energy is there, I'll try to be as soon as possible. I'll try to reply back.
Sabil sir, can I?
Sure.
Yes.
Dear, okay, so just want to thank all of us. Dear speaker, Dr. Rajiv Maiti sir, our students and the faculty members. Today we had a very nice talk on water resource and climate change. Rajiv sir has explained nicely different modeling aspects on hydrology, rainfall, the pattern of rainfall, how it is changing over the past few years, and also about the droughts, how the drought pattern is changing and how we can model this, right? So I'm sure that we gained a lot of knowledge from this talk. So I sincerely thank Dr. Rajiv Maiti sir for accepting our invitation and delivering this beautiful talk. I thank Dr. Sabil sir and Dr. Shomakanta sir for organizing this event. I thank our HOD sir, Dr. Parameshwaram sir, and our other faculty members for attending this talk. And finally, I want to thank all the students for attending this talk, and have a nice evening. Thank you very much.
And I also want to thank all of you, particularly the organizers, for inviting me and giving me this opportunity to deliver my talk here. I try to be as basic as to the students, but you can understand that given this research domain, it is now in the active research domain now. But I hope that they will be able to keep these things sometime in the future. It will be more useful to them. Once again, I want to thank to all the faculty members, HOD of this, the head of this department. Thank you, everyone. Thank you.
Thank you so much, sir.
Thank you, sir.
Thank you very much, sir.
So should I leave the meeting now? Should I click the hang up?
Yes.
Or? Okay.
Thank you very much,
Then
sir. Yeah.
Thank you.
bye everyone.
Okay, bye. Take care.